Welcome to this walkthrough of LeetCode problem number 1803, count pairs with XOR in a range. In this video, we'll explore how to efficiently solve this problem by analyzing the constraints, leveraging optimal data structures, and breaking the solution into digestible steps. Stick around to deepen your understanding of XOR-based problems and enhance your problem-solving skills. In this problem, we are tasked with finding the number of good pairs in a given array. A pair, represented as I, j, is defined as good if two conditions are met. First, the indices must satisfy the inequality 0 equals I less than j nums.length. Second, the XOR operation between the values at these indices, nums, I, XOR nums, j, must lie within the specified range, low, high. The input consists of an array nums of integers, where the size of the array can go up to 20,000 elements, and each element can have a value up to 1 million. Additionally, the range bounds low and high are integers that satisfy 0 equals low equals high equals 10⁻6. The output is a single integer representing the count of such good pairs that meet these criteria. The problem requires us to handle large input sizes efficiently, which makes optimization a critical aspect of the solution. Let's take a look at an example to better understand the problem. Suppose we have nums equals 1, 4, 2, 7, with low equals 2 and high equals 6. Our task is to count how many pairs of indices, I, j, meet the conditions. First, we compute the XOR values for all possible pairs. For example, 0, 1, corresponds to 1 XOR 4 equals 5, which lies within the range, 2, 6, so it is a good pair. Similarly, 0, 2, gives 1 XOR 2 equals 3 and 0, 3, results in 1 XOR 7 equals 6, both of which are also within the range. Continuing this process, we find that the pairs 1, 2, 1, 3, and 2, 3 also satisfy the criteria. Summing them up, we get a total of 6 good pairs for this input. This example highlights the importance of efficiently iterating over the array and evaluating the XOR values for all valid index combinations. Now, consider another example where nums equals 9, 8, 4, 2, 1, low equals 5, and high equals 14. Here, we again calculate the XOR values for all valid pairs. For instance, 0, 1, results in 9 XOR 8 equals 1, which is not within the range, 5, 14, so it is not a good pair. However, 0, 2, gives 9 XOR 4 equals 13, which is within the range, making it a good pair. Similarly, 0, 3, results in 9 XOR 2 equals 11, and 0, 4, gives 9 XOR 1 equals 8, both of which are good pairs. We continue this process for all other index combinations, such as 1, 2, and 1, 3, both of which also result in XOR values within the range. By systematically evaluating all pairs, we ensure that no valid combination is missed. Completing the calculations for the example, we find that 1, 4 results in 8 XOR 1 equals 9, which is in the range, 5, 14, and 2, 3 gives 4 XOR 2 equals 6, which also qualifies as a good pair. Finally, 2, 4 produces 4 XOR 1 equals 5, which is valid, whereas 3, 4 results in 2 XOR 1 equals 3, which is outside the range and therefore not a good pair. Summing up, we find that there are 8 good pairs in total for this input. It's important to note the constraints of the problem, such as the potential for very large arrays or values, which require an efficient approach to avoid excessive computation. Additionally, edge cases like arrays of length 1, where no pairs exist, or scenarios where all XOR values fall outside the range, must be handled appropriately to ensure the solution is robust and performs well under maximum constraints. To tackle the problem of counting pairs with XOR in a given range, we start by understanding the requirements. The goal is to find all pairs of indices, I, j, where 0 equals I less than j nums.length, and the XOR of their corresponding values, nums, I, XOR nums, j, lies within the range, low, high. A straightforward solution to this challenge is the brute force approach. Here, we iterate over all possible pairs of indices, compute their XOR value, check if it falls within the specified range, and increment the count accordingly. While this method is intuitive and simple to implement, it involves 2 nested loops, resulting in a time complexity of O, n superscript 2. For large input sizes, such as when n approaches 10,000, this approach becomes computationally prohibitive. Thus, while the brute force method serves as a good starting point for understanding the problem, it highlights the need for a more efficient solution to handle larger constraints effectively. A more efficient strategy to solve the problem is the tree-based optimized approach. This method is built on the observation that XOR operations are inherently bitwise, making it possible to use a binary tree, or prefix tree, to store and query binary representations of numbers. A binary tree is structured such that each node represents a single bit, either 0 or 1, which allows for efficient storage and retrieval of numbers in their binary form. The key idea here is that for any number x in the array, we can use the tree to count how many previously inserted numbers, when XORed with x, produce a result within the range low, high. The process involves inserting numbers into the tree while iterating through the array, and at the same time, querying the tree to find valid pairs. By leveraging the properties of XOR and the binary tree structure, this approach significantly reduces the problem's complexity. Instead of the O and superscript 2 time required by brute force, the tree-based method operates in O and asterisk log C, where C represents the maximum value of numbers in binary form. This makes it highly efficient and scalable for larger inputs, though it does require more complex implementation details. Other potential strategies for solving this problem were also considered, such as using a hash map to store XOR results or sorting the array and leveraging binary search for range queries. However, these alternatives fall short in terms of efficiency. Hash maps, for example, struggle with handling the range constraints effectively, while sorting-based methods introduce additional overhead that makes them less optimal for this scenario. After evaluating these options, the tree-based optimized approach emerged as the clear choice due to its ability to balance efficiency and scalability. Although it is more complex to implement compared to brute force or simpler alternatives, it is the only approach that meets the problem's constraints and performs well even with larger inputs. The breakthrough insight here was recognizing that the properties of XOR align naturally with the structure of a binary tree, enabling efficient range queries. By representing numbers as binary strings and leveraging bitwise operations during tree traversal, we can achieve the desired efficiency while keeping the solution scalable. When comparing the different approaches, we see a clear trade-off between simplicity and efficiency. The brute force method, while easy to implement, is impractical for large inputs due to its O and superscript 2 time complexity. The tree-based approach, on the other hand, offers an efficient O and asterisk log C solution, making it suitable for handling larger constraints, though it requires a more sophisticated implementation. Alternative strategies, such as using hash maps or sorting combined with binary search, struggle with range queries or introduce additional computational overhead, making them less effective for this problem. Ultimately, the tree-based approach stands out as the most balanced solution, providing the necessary performance without sacrificing scalability. This choice underscores the importance of aligning the properties of the problem, in this case, XOR operations and binary representations, with an efficient data structure like a binary tree to achieve the optimal result. To solve this problem, we need to count the number of pairs in the array such that the XOR of the two numbers lies within a given range. While a brute force approach would involve checking every possible pair, this results in quadratic time complexity, which is inefficient for large arrays. Instead, we can leverage some key insights to design a faster solution. First, we use the properties of XOR. For instance, the relationship a XOR B equals C allows us to derive a XOR C equals B and B XOR C equals A. These properties are important because they let us manipulate the XOR equation to find missing values efficiently. Additionally, we use a binary tree data structure to store the binary representations of numbers. This tree allows us to efficiently navigate and count numbers that satisfy the XOR range condition. By combining these insights, we can avoid explicitly iterating over all pairs and instead compute the result in a much more optimized way. The algorithm can be broken down into several steps. First, we initialize a binary tree. This tree consists of nodes where each node corresponds to a binary digit, either 0 or 1, and each node also keeps account of how many numbers pass through it. Next, we insert the numbers from the array into the tree. To do this, we traverse the binary representation of each number, bit by bit, and insert it into the corresponding child node in the tree, incrementing the count at each step. Once the numbers are in the tree, we can count valid pairs. For each new number we process, we calculate its XOR with the numbers already in the tree and determine how many of these results fall within the given range. This is accomplished by traversing the tree and leveraging the stored counts to efficiently check the range condition. Finally, we handle edge cases, such as ensuring the tree accounts for the full range of binary representations, including leading zeros, and properly managing boundary conditions like when the range starts or ends at 0. The binary tree is a crucial data structure for this algorithm. Each node in the tree represents a binary digit, either 0 or 1, and the tree's depth corresponds to the number of bits and the largest number we are working with, typically 32 bits for integers. To facilitate efficient range queries, we maintain counters at each node to track how many numbers pass through that node. This allows us to perform quick calculations while traversing the tree. In terms of complexity, the time complexity of the algorithm is O(n*log, max_number, where n is the size of the array and max_number is the largest number in the array. This is because we process each number bit by bit. The space complexity is also O(n*log, max_number, as we need to store the binary representations of the numbers in the tree. For example, if our input array is 1, 4, 2, 7, and the range is 2, 6, we start by converting each number to binary and inserting them into the tree. As we process each number, we calculate its XOR with previously inserted numbers and check if the result falls within the range. This approach allows us to efficiently count valid pairs without explicitly iterating over all possibilities. Here, we begin by defining a tree node class to represent each node in our tree data structure. Each node has two attributes: children, which is a dictionary to store child nodes for the binary bits 0 and 1, and count, which keeps track of how many numbers pass through this node. Next, we move to the solution class, where we define the main function countPairs. Inside this function, we first define an insert helper function, which is used to insert a number into the tree. For each bit in the 16-bit representation of a number, starting from the most significant bit, we calculate the bit value by right-shifting the number and applying a bitwise AND operation. If the bit value is not already in the current node's children, we create a new tree node for it. Then, we update the current node to this child and increment its count. This process ensures that the tree stores the binary representation of all numbers, along with the count of numbers that pass through each node. The next helper function, count<= calculates how many numbers in the tree have an XOR with the given number less than or equal to a specified value x. Starting from the root of the tree, we traverse bit by bit. For each bit, we determine the current bit of the number and the corresponding bit of x. If the target bit of x is 1, we add the count of numbers in the branch that matches the current numbers bit, as these numbers would contribute to a valid XOR less than or equal to x. We then move to the opposite branch, if it exists. If the target bit of x is 0, we simply follow the branch that matches the current numbers bit. After defining these helper functions, we initialize an empty tree and a count variable. For each number in nums, we calculate the count of pairs with XOR in the range by subtracting the result of count<= 4 low 1 from the result 4 high. This gives the count of numbers with XOR in the desired range. Finally, we insert the current number into the tree to update it for subsequent iterations. At the end, the total count is returned. Here, we start by defining a tree node class, which represents the structure of our tree. Each tree node has a map called children to store its child nodes and a count variable to track how many numbers pass through this node. The constructor initializes these fields. Next, we define the solution class, where the root of our tree is declared as a private variable. The main method, countPairs, takes an array of numbers and two integers, low and high, as input. The goal is to count pairs of numbers whose XOR lies within the given range. We initialize the root node and a variable count to 0. Then, for each number in the array, we compute the count of numbers that, when XORed with this number, fall below high and subtract those that fall below low 1. This difference gives the count of pairs within the range for that number. After calculating this, we insert the number into the tree for future comparisons. Finally, the total count is returned. To support the countPairs method, we define the insert method. This method takes an integer number and inserts its binary representation into the tree. Starting from the most significant bit, we extract each bit using a bitwise operation. If the bit does not exist in the current node's children, we create a new tree node for it. We then move to the child node corresponding to this bit and increment its count to reflect the addition of a number passing through. This ensures that the tree is updated with the binary structure of number. Next, we define the count less than or equal method to count how many numbers in the tree have XOR values less than or equal to a given value x when XORed with the input number. We traverse the tree bit by bit, comparing the bits of x in number. If the current bit of x is 1, it means we can include numbers that match the current bit of number and then explore the opposite branch for smaller values. Otherwise, we continue along the branch that matches number. The traversal continues until we either exhaust all relevant bits or the current node becomes null, which happens when no further matches are possible. During this process, we accumulate the count of numbers that satisfy the condition into the count variable. At the end of the traversal, the count is returned, representing the number of elements in the tree that, when XORed with number, yield a result less than or equal to x. This method is critical for efficiently calculating the number of valid pairs within the given range. Together with the insert method, it allows us to use the tree structure to quickly evaluate XOR conditions and manage the input array and logarithmic time complexity for each number. To solve this problem, we use a tree data structure, which helps us efficiently count the number of pairs with XOR values falling within the given range. Let's start with the example where nums equals 1, 4, 2, 7, low equals 2, and high equals 6. First, we initialize an empty tree. The root of the tree is represented by a tree node, and this will serve as the foundation for our subsequent operations. Next, we iterate through each number in the array and calculate how many valid pairs it forms with numbers already in the tree. For the first number, 1, we calculate the count of numbers that would yield an XOR result less than or equal to 6 and less than or equal to 1. Since the tree is empty, both counts are 0, and 1 does not contribute any pairs at this stage. We then insert 1 into the tree by traversing its binary representation from the most significant bit to the least significant bit. For each bit, we create new nodes as necessary and update the count at each node to reflect the insertion of this number. Now we process the next number, 4. To calculate the pairs contributed by 4, we first find how many numbers in the tree yield an XOR result less than or equal to 6 with 4, and this count is 1. This corresponds to the pair 1, 4. Similarly, we calculate the count of numbers that yield an XOR result less than or equal to 1 with 4, and this count is 0. Subtracting these, we see that 4 contributes one valid pair. After this, we insert 4 into the tree. The binary representation of 4 is traversed, and we create or navigate through the necessary nodes, updating the counts at each step. Next, we process 2. For this number, we calculate the count of numbers in the tree that yield an XOR result less than or equal to 6 with 2, which is 2. These pairs are 1, 2, and 4, 2. The count for XOR results less than or equal to 1 is 0, so 2 contributes a total of 2 pairs. Finally, we insert 2 into the tree, following the same process of traversing its binary representation, creating nodes, and updating counts. The last number in this example is 7. To determine the pairs contributed by 7, we calculate the count of numbers in the tree that yield an XOR result less than or equal to 6 with 7, which is 2. These pairs are 4, 7, and 2, 7. We also calculate the count for XOR results less than or equal to 1 with 7, which is 1, corresponding to the pair 1, 7. Subtracting these counts, we find that 7 contributes one valid pair. After this, we insert 7 into the tree by traversing its binary representation and updating counts at each node. At this point, all numbers have been processed, and we sum up the pairs contributed by each number, which are 0, 1, 2, and 1. This gives us a total of 4 pairs for this example. Let's move to the next example, where nums equals 8, 10, 2, low equals 6, and high equals 15. We start by initializing an empty tree. The first number is 8, and we calculate the count of numbers in the tree that yield an XOR result less than or equal to 15 with 8. Since the tree is empty, this count is 0. Similarly, the count for XOR results less than or equal to 5 with 8 is also 0. Therefore, 8 does not contribute any pairs at this stage. We then insert 8 into the tree by traversing its binary representation and creating nodes as needed, updating counts along the way. Next, we process 10. The count of numbers in the tree that yield an XOR result less than or equal to 15 with 10 is 1, corresponding to the pair 8, 10. The count for XOR results less than or equal to 5 with 10 is 0. Subtracting these counts, we find that 10 contributes one valid pair. We then insert 10 into the tree, updating nodes and counts as we traverse its binary representation. The final number in this example is 2. We calculate the count of numbers in the tree that yield an XOR result less than or equal to 15 with 2, which is 2. These pairs are 8, 2, and 10, 2. The count for XOR results less than or equal to 5 with 2 is 0. Subtracting these, we see that 2 contributes two valid pairs. After this, we insert 2 into the tree, navigating its binary representation and updating counts at the necessary nodes. Summing up the contributions from each number, we get 0 from 8, 1 from 10, and 2 from 2, giving us a total of 3 pairs for this example. In the third example, nums equals 0, 1, 2, 3, low equals 1, and high equals 3. We begin by initializing an empty tree. The first number is 0, which does not contribute any pairs since the tree is empty. We insert 0 into the tree, updating counts at each node as we traverse its binary representation. Next, we process 1. To calculate its contributions, we find the count of numbers in the tree that yield an XOR result less than or equal to 3 with 1, which is 1. This corresponds to the pair 0, 1. The count for XOR results less than or equal to 0 with 1 is 0. Thus, 1 contributes one pair. We then insert 1 into the tree. For 2, the count for XOR results less than or equal to 3 with 2 is 2, representing the pairs 0, 2, and 1, 2. The count for XOR results less than or equal to 0 with 2 is 0, so 2 contributes two pairs. After inserting 2, we process 3. The count for XOR results less than or equal to 3 with 3 is 3, corresponding to the pairs 0, 3, 1, 3, and 2, 3. The count for XOR results less than or equal to 0 with 3 is 0, so 3 contributes 3 pairs. After processing all numbers in this example, we calculate the total pairs by summing the contributions from each number 0 from 0, 1 from 1, 2 from 2, and 3 from 3. This gives us a final total of 6 pairs. With this, we have completed the walkthrough of the third example, demonstrating how the tree helps efficiently count pairs with XOR values within the specified range. Here, we start by analyzing the time complexity of our solution. First, consider the insertion of numbers into the tree. Each number is processed bit by bit, starting from the 15th bit down to the 0th bit, since we are working with 16-bit integers. For every bit, we either follow an existing path in the tree or create a new node, and this takes a constant amount of time, specifically 16 operations per number. If there are n numbers in the input array, the total cost of inserting all the numbers is n*16, which simplifies to n. Next, we analyze the process of counting pairs with XOR values within the given range. For each number, we traverse the tree to calculate how many numbers already inserted satisfy the XOR condition, and this traversal also takes 16 operations per number. Again, for n numbers, the total counting cost becomes n*16, which simplifies to n. Now, combining the insertion and counting operations, the overall time complexity of our approach is n. Both operations involve processing each number in the input array with a fixed cost per bit, which leads to a linear relationship with the size of the input. Shifting to space complexity, the main contributor is the tree structure used to store the binary representations of the numbers. Each number, consisting of 16 bits, can potentially create a new path in the tree. In the worst case, where all numbers are unique, this results in n numbers creating up to n*16 nodes in total. Since each tree node requires a constant amount of memory for its children and a count variable, the space usage per node remains 1. Thus, the overall space complexity for the tree becomes n*16, which simplifies to n. Additional space usage, such as for variables and function calls, is negligible in comparison, contributing only 1. The overall space complexity is therefore dominated by the tree, resulting in n. Comparing this optimized tree-based approach to a brute force method is insightful. The naive solution involves iterating over all pairs of numbers and calculating their XOR values to check if they fall within the given range. This would require n² time, as we would examine every possible pair. However, the space complexity of the brute force approach is only 1, because it does not rely on auxiliary data structures. In contrast, the optimized tree-based solution significantly reduces the time complexity to n, by eliminating the need to evaluate every pair explicitly. Although the space complexity increases to n due to the tree, this trade-off is highly efficient for large inputs, where the time savings are far more impactful. When we analyze the best, average, and worst cases of this solution, the efficiencies remain consistent. In the best case, where all the numbers in the array are identical, the tree will have minimal nodes, as repeated numbers do not create new paths. The traversal cost for each number is unaffected, so the time complexity stays n, but the space usage drops to 16 for the tree. In the average case, where numbers are randomly distributed, the tree grows in proportion to the size of the input, resulting in both time and space complexities of n. Even in the worst case, where all numbers are unique, the tree grows to its maximum size of n*16 nodes. Despite the additional space required, the time complexity remains n, as we still process each number in constant time per bit. Finally, we can mathematically validate the linear complexity of this solution. For each number, insertion and counting operations involve processing 16 bits, leading to a total time proportional to 16*n, which simplifies to n. Regarding the size of the tree, its growth depends on the number of unique numbers in the input. Each number contributes at most 16 nodes, so the total tree size is n*16, which simplifies to n. This confirms that both the time and space complexities scale linearly with the size of the input, making the solution highly efficient for large datasets. When solving this problem, there are several common mistakes to watch out for. First, attempting a brute force solution with nested loops to calculate XOR for all pairs might seem straightforward, but it's highly inefficient. With a time complexity of n², this approach quickly becomes impractical for larger inputs, such as arrays with lengths up to 10,000. Next, failing to use the prefix XOR optimization is another frequent issue. The key property here is that the XOR of two indices can be derived using the prefix XOR array, avoiding redundant calculations. Without leveraging this, solutions often end up with unnecessary computational overhead. Another pitfall is misunderstanding the range condition, where the XOR value must satisfy low less than or equal to XOR less than or equal to high. Misinterpreting this and neglecting either bound, or using an exclusive range, leads to incorrect pair counts. Lastly, if you're using a tree-based approach, mismanaging binary representations is a common error. For example, not padding numbers to 31 bits can cause mismatches in the tree structure, preventing it from accurately representing XOR relationships and leading to traversal issues. Overcomplicating tree queries is another common mistake. While the tree approach is powerful, adding unnecessary complexity to its operations can lead to bugs and make debugging more challenging. Simplifying and modularizing your tree operations ensures that the solution is not only efficient but also easier to manage. Now, let's discuss some interview insights. First, it's essential to deeply understand bitwise operations and XOR properties. For example, knowing that a XOR equals 0 and a XOR 0 equals a can help you simplify calculations. The tree-based approach is particularly effective for this problem, offering an efficient solution with a time complexity of n*log, max_number, by working directly with the binary representations of numbers. However, interviewers may ask you to compare it with the prefix XOR and hashmap approach. While the tree is more space efficient, the hashmap method is often simpler to implement, though it may be less consistent in performance. Lastly, always emphasize edge cases during interviews, such as handling arrays with duplicates, single-element arrays, or extreme range values like low equals 0 and high equals 10 to the power of 9. This problem is closely related to several others, making it a great opportunity to strengthen your understanding of XOR-based algorithms and tree data structures. For instance, problem number 421, maximum XOR of two numbers in an array, focuses on finding the largest XOR value using a similar tree-based approach. Problem number 1707, maximum XOR with an element from array, combines efficient tree traversal with constraints to maximize XOR values. Additionally, problem number 1310, XOR queries of a subarray, leverages the prefix XOR technique to compute XOR values for subarrays efficiently. Lastly, problem number 208, implement tree, prefix tree, is foundational for understanding how tries work, which is central to solving this problem. Now, let's discuss the tree-based approach in more detail. Here, you build a tree to hold binary representations of the numbers in the array. By traversing the tree, you can efficiently count pairs with XOR values in the specified range, low, high. This method has a time complexity of O, an asterisk log, max_number, making it both space-efficient and scalable. However, it does require careful implementation, especially when managing the binary representations of numbers. An alternative to the tree-based approach is using prefix XOR with hash maps. In this method, you calculate prefix XOR values and use a hash map to count occurrences of XOR differences that satisfy the condition low less than or equal to XOR less than or equal to high. While this approach has an average time complexity of O(n), it can degrade to O(n) squared in the worst case, typically due to hashing collisions or skewed input distributions. The trade-offs here are simplicity versus performance consistency, as the hash map method is easier to implement but less reliable under certain conditions. Finally, there's the brute force approach, where you directly compute XOR for all possible pairs and count those that fall within the range, low, high. This has a time complexity of O(n) squared, making it impractical for larger inputs. Brute force is only suitable for small arrays due to its inefficiency. Each of these approaches has its strengths and weaknesses, and understanding their trade-offs is essential for selecting the right one based on the problem constraints. Great job making it to the end. To recap, we covered an efficient approach leveraging tries to solve XOR-based pair counting problems. Remember, understanding data structures like tries can make a big difference in solving range queries. If you enjoyed this, don't forget to like, share, and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!